Hello, everyone. Welcome to today's presentation on quick disconnects for liquid cooling, design, specification, and implementation. My name is Elizabeth Langer. I'm the R&D Engineering Manager for the Thermal Management Business Unit within CPC. The goal of the presentation today is to provide a high-level understanding of the current state of liquid cooling technology in the industry, benefits, methods, and key considerations for successful implementation and reliable deployment. And then, of course, quick disconnects being an integral component of data center thermal management, we're going to introduce and discuss some of the fundamental considerations for designing and optimizing quick disconnect performance in cooling systems, touching on materials of construction, chemical compatibility, valve design, and pressure loss should provide a good baseline to help enable engineers during that specification process. So why liquid cooling and why liquid cooling now? We've seen with advancements in the semiconductor technology over the years, shifts in power consumption and consequently associated cooling requirements. But now in recent years, we're yet again in a place where compute power and certainly the compute densities have really reached the limits of efficient thermal management with traditional air cooling approaches. So now that liquid cooling is becoming more widely considered, data center and colocation providers can begin to realize a number of benefits in the form of energy savings, improved PUE metrics, cost savings, the ability to dramatically increase densities, and of course, noise reduction. If you've ever been in an air-cooled facility, you know that the fans have a significant impact on the working environment. Within industry, there's been quite a bit of activity over the last few years to really educate and develop best practices across the industry with regard to liquid cooling technologies for high performance computing, data centers, and colocation facilities. So here we have a kind of a representative architecture scoped out from left to right by a rear door heat exchanger to a direct contact cold plate and all the way to full bath immersion. It's interesting to note that the intent with the segmentation of these technologies isn't that they're mutually exclusive, but really on a case-by-case basis, there might be some overlap. A facility might require one over another, or potentially hybrid approach implementing multiple cooling technologies in one system. A rear door heat exchanger in tandem with direct contact cold plate structure, for example. So supporting that liquid cooling architecture, there's a variety of subsystems and components that are really critical to successful and reliable operation of the cooling system. The components themselves, as well as interactions and dependencies between them, warrant detailed analysis during design and specification. So starting with the coolant, there's considerations to be made around certain additives that might be needed to ward off corrosion, biofouling, et cetera. Viscosity and specific gravity are certainly going to play into considerations around pumping power, and certainly the reliability and redundancy of the pumps are going to be key. Manifolds, heat exchangers, cold plates, all tie into the overall system performance and require detailed analysis with regard to flow rates and pressure. Certainly filtration and debris are going to be a consideration for those components as well. And then tubing and quick disconnects are really the way to connect all that together. So the point here, I guess, is that every component within a liquid cooling system matters, and it's really important to think holistically throughout that design process. Within a data center or other electronics cooling system, there will typically be two fluid circulating loops with a CDU barrier, a coolant distribution unit barrier between them. On the facility water system side, or FWS, there may be fewer connections, larger plumbing and fittings to support really high volumes of fluid. On the TCS, or technology cooling system side, where the IT equipment resides, the cooling architecture, such as rear door heat exchangers, that direct contact cold plate, or full bath immersion, will use many more connections and require more detailed consideration around specifications. The closer to the IT equipment, the more critical the quick disconnects performance and reliability becomes. Now, with an understanding of where quick disconnects might be installed within a data center facility and the importance of their performance and reliability as they get closer and closer to the IT equipment, we can dig a little deeper and understand some of the key parameters of importance for specification. When thinking about the anatomy of a quick disconnect, we can kind of break it out into 3 high-level categories for consideration when selecting the right quick disconnect. Material selection is a very important factor to consider early on, both from a structural and mechanical viewpoint, but equally important with regard to chemical compatibility. Ensuring all wetted materials that will be in contact with coolant, as well as other component materials within the loop that may have an interaction. Understanding of and visibility to various configuration options related to mating and mounting will enable designers to fully optimize the performance, as well as provide flexibility in promoting usability and serviceability of the system. And finally, valving and shutoff characteristics of the quick disconnect are really imperative for designing an efficient and reliable system. Quick disconnects can be comprised of a variety of materials, metals or polymers, and can be effective with any combination of those three. So metals, we consider alloys that might be brass, aluminum, certainly a stainless steel, looking for corrosion resistance, strength. Depending on the alloy, you might need a certain surface treatment, maybe a nickel chrome plating on a brass, a heat treatment, oxidative or passivation to a stainless steel. Plastics, same thing, looking for mechanical strength, certainly chemical compatibility, flame retardants, UL94, hydrolytic and thermally stable thermoplastics, and certainly lightweight is an advantage. In addition to those structural and mechanical characteristics, it's important to understand other physical characteristics such as chemical compatibility, resistance to corrosion, resistance to fluid erosion. We really want to consider all materials that are going to be in that wetted fluid loop. Coolant compatibility is especially important when discussing and considering elastomeric seals and O-rings for quick disconnects. Galvanic corrosion is certainly a key consideration when there are dissimilar metals that are in contact with a conductive fluid. Metals such as, for example, aluminum and copper that are on the opposite end of the electric potential scale might have a tendency to create sort of a battery in the system. Flow path erosion can be a consideration when there's extremely high fluid velocities going through small orifices, and certainly environmental exposures are all things to consider when specifying. Many quick disconnect configurations exist on the market and can often be customized to fit the unique needs of a specific application. So things to consider there are the way that the quick disconnect mates with itself. So it could be a blind mate connection where it might be mounted on the back of a server or a blade, or a hand mate where it might be out on the front, and then a technician needs to actuate either a ball and sleeve mechanism or a thumb latch mechanism to make and break that connection. There's different valve types to consider, non-spill versus more of a wet break style poppet valve. So non-spill valves, when you go to connect and disconnect, are really going to be really true dry break connections. There might be a little bit of a wetted surface, but no drips. Wet break, you might experience a small volume of fluid on disconnection. And then termination. So will the quick disconnect be threaded into a manifold? Will it need to terminate to tubing or anything in between there, really? Alongside manifolds, tubing, piping, cold plates, quick disconnects are really a key consideration when analyzing a full flow network model for your system. They can have a really critical impact on system flow and pressure loss. From more of an electronics background here, we can kind of consider the hydraulic analogy to describe some of these considerations for optimizing fluid flow. So you can liken voltage to fluid pressure, directly relating to capacity and the ability to do work. Current can also be likened to a fluid flow rate. How fast can we do the work? We know that the rate of heat transfer is directly related to the mass flow rate. So higher flow means more heat can be moved. That being said, it's not always practical from a system efficiency and safety standpoint to simply increase the pressure and flow. And so careful analysis upfront of the impact of the quick disconnect on overall system performance is critical. Additionally, we've seen on the right-hand side from our friend Bernoulli, we can understand the relationship of fluid velocity to fluid pressure. As the fluid velocity increases, for example, when flow through tight spaces and small orifices, the fluid pressure will actually decrease, contributing to the overall system pressure loss. And vice versa, as the flow becomes less restrictive, the fluid velocity will decrease and pressure will stabilize. This concept is fundamental to understanding and being able to really optimize flow paths within quick disconnects to produce the least possible pressure loss across that valve set. A nice way to characterize that pressure loss associated with a quick disconnect or really any valve set is to use what's called the flow coefficient, or CV. And this is a metric that's representative of the volumetric flow rate for which 1 psi of pressure would be lost. So here we can see on the chart at 1 psi, if we navigate over to the right, that would correlate to 1.4 gallons a minute. And vice versa, or I suppose in imperial terms, we can reference what's called a kV, which would be 0.86 of what the CV is, and that's representative of bar or meters cubed per second. This equation is, or this metric is a function of the volumetric flow rate, the specific gravity of the fluid, and the overall pressure loss of the system. So one thing to note here is that published and catalog CVs are typically reported with water, which has a specific gravity of 1, making that equation pretty simple to evaluate. So we want to make sure we use correction factors and the correct specific gravity when using coolants other than water. Now that we've got a pretty good handle on the anatomy of the quick disconnect, I want to introduce some of the key functional requirements. So some ways to characterize quick disconnects too with regard to performance are related to spillage, volume of fluid on disconnect. We talked earlier about non-spill versus wet break valves. Inclusion, the volume of air that's introduced into the fluid loop on connection. And then, of course, leaks, so unintentional fluid discharge that can really be potentially catastrophic in the event that it does occur. There are some ways to mitigate and enhance seal efficacy and reliability are multi-lobe seals and certainly redundant sealing options that can all help protect and mitigate the occurrence of a leak. Additionally, things to consider around temperature, that would be resistance to low and high temperatures, certainly stability across the range of temperatures that we'll be operating under, as well as storage and shipping considerations. Flammability, so consider UL 94 rated materials. One thing to note is that thermoplastics such as PPSU are inherently flame retarded, non-halogenated, so there's no bromine or chlorine or any other SVHCs in there that are going to be hazardous to your system. Thermal conductivity, metal quick disconnects could, of course, be hot to the touch if there's a hot fluid circulating. So consider the location and operator interaction that might be in place. And then chemical compatibility, as we discussed earlier, all of the wetted materials in the fluid loop, and really want to consider that for long-term service and exposure. In summary, we can characterize all these different parameters of importance and really make sure that we're taking a holistic view at the system on a high level. So with all the system requirements locked in, engage with experts, with quick disconnect experts surely and really dig into those details. Parameters of importance can be referenced through an OCP ACS document, cold plate liquid cooling requirements white paper that's available publicly. For more information, you can certainly reach out to me. I've got my email and phone number below, or my colleague Barry Nielsen, who's Applications Development Manager with CPC. Thank you for attending today. Hopefully you learned something.